Oh, okay.
And the screen looks like it's only half.
Yeah. Okay. It's a great pleasure to have Professor Siu-Hung Ng, Richard from Louisiana State University to visit BIMSA today. He will give a talk about mining for modular data from congruence representations. Welcome.
Thank you very much for the invitation, and I really appreciate your hospitality. You visit here. So my talk here, actually, some of the talk actually I presented last year. That was about rank 8. Now it may come to rank 11 or even higher. So maybe some of the material I presented before, and there were some used more recently. So this talk actually I presented in Hong Kong, so I didn't prepare another talk for the Senate. I was informed 2 days ago I need to give a talk. Please excuse me. This is the joint work with Eric Rowell, Zhenghan, and Wang. So the goal of this project is to find modular data from representation. So from a very primitive or common knowledge of the character representation to see, and then you carry how to get to the modular data if you can get it. So let me start with the modular group first. This is fundamental. I want all of you agree with my convention, at least understand my convention. So the modular group means SL2C, which is the group of 2 by 2 integer matrix of determinant 1. And it is generated by 2 matrices, like this. X I call inversion, D is called translation. So these 2 matrices do not generate a whole group. And you can actually make it to be the generator with relation. This is actually the generator representation of the modular group. It's generated by S and T symbolically. Doesn't matter you have this 2 here, but symbolically generated by S and T raised to the power 3 S squared and S2 4 1. So that means as long as I have to, this is basically the notion of representation now. If I have a representation, maybe I just go down to the next step. If I have a representation, I only need to know the image of S and the image of T, which satisfy this relation. Then it will give you a representation. This is the key for this presentation. I don't need to check any, but the only part is I don't know much about them. Almost nothing. Using the generator relation to write down representation, you can write down rigorously, but you don't know anything. So I'm particularly interested in congruence representation because I was interested in modular data. So a representation called congruence means like it vector through a finite modular group. So again, because it is a representation, SL2C only need to look at the image of that image all the time. So only need these 2 matrices to determine the representation. So the keyword is congruence here in this. Any question? Fun. Now I just tell you the motivation here and also why we do. So I like the representation like vertex operator algebra. So this is more or less the beginning of the whole story. Associated to a rational component free field. Usually you talk about a nice vertex operator algebra. It has a representation of SL2. This representation actually is dimension R. R is indeed the number of primary field or the irreducible V module. Whatever V is some kind of algebraic object with representation and simple object. But the difference is that this V as an algebra, which is a greater vector space, then you take a homogeneous element V of degree K, And you can write that, and for each simple module M, you can write down a morphic function. I call it chi MV tau. On the other hand, you can write it defined on the plane. And this is a black box here. Let's put it this way. Give me an object give me an element in V, and give me a simple module, then I can write down a function for that. So now then I collect all the simple module of V, and then write rho G as this gamma ij. So G is any element in SL2C. So any element there is A, B, C, D. So therefore, like I just write there. And it satisfies this relation. You take the character function of Mj, V is still there because this is one of the input, and you write down the Mobius transform of the entry tau, and you write the other side as a linear combination together with this the factor there. So in fact, if you move the factor to the left, you get here a representation of SL2Z. So this is actually called module invariance. It's a famous result too. So the how it begins is basically this. I would say again from this one. So this result tells us that if you put all these functions together into vector function, and this vector function is stabilized by SL2Z by using the Mobius transform, and also this factor C tau plus D. So this how it related to vector value modular form and VOA. So each VOA gives you a vector value modular form. So what was not known is that, or what was open is that this pair function are very actually concurrent. Do they fix by the concurrence of SL2Z? So, or the actual representation SL2Z. So this is the result that we proved with Dong, Lin, and myself. The representation SL2Z associated with a nice VOA is a concurrence representation. That means the whole thing is vector through the SL2 and Z. So the kernel is a principal concurrence contain the principal concurrence of the. Hence the character. This actually was open. The character function is a concurrent modular form. So what happened is if the concurrent modular form, each of them has a very nice coefficient if you the Fourier expansion. For example, the bounded denominator problem. That means like you multiply a triple scalar to the function that I mentioned. If the function expanding Fourier transform, all the coefficients are within. So these are a strong property. The concurrence is a strong property. We know that. We cannot. But this is actually not a VOA result. I shouldn't say it's a VOA result, but come from the category. So go back to the reason why it works is because a result of Lapowski and Wang. Basically, they say the V is nice, then the module category V is a module. I used to work modular fusion category, but in the past they call it modular tensor category. I could flex it. In the past, almost a year ago. Doesn't matter. It just they just emphasize the fusion category. So what is the modular fusion category? Which is like in short, it is a fusion category. First of all, I give you the notion of fusion category first. I think maybe you know that. Just record. So a fusion category is a semi-simple rigid linear being monoidal category. Bunch of adjective there. The word semi-simplicity has to be mentioned. The rigidity, linearity is the Albanian kind of irrelevant because it's semi-simplicity. One thing we need is like they're only finding many simple objects. I mean, up to isomorphism. And then the unit object is required to be simple. So if one is not simple, we call it multi-function. Anyway, so we won't touch that basically, but we need something more delicate, which is the modular part. And there's a notion in between that we call it like ribbon, but I just jump over it. So a fusion category is called modular if it admits a braiding. This is probably a braiding. This is the natural isomorphism. A tensor B, B tensor A, scope A B. Then I usually draw this kind of thing to denote this map. So you just draw pictures. So, but then because of that, you can compose. So you can do this. AB, then we'll go back to AB. So it's endomorphism. So particularly the S matrix defined by just this, taking the trace. Well, what does it mean by trace? Trace means like I can close it. That's it. You can close it simply because there's a ribbon structure there. You can close it any way you like. So any kind of this knot is represented by a number. So when I take trace, F actually is given by trace of these agents. And then there's a ribbon structure here. The ribbon structure is necessary because I cannot close it without the ribbon structure. You can say the ribbon structure is some kind of a way to allow you to have measurement, because the ribbon structure and the spherical structure are the same once you pick the braid. They means they correspond to each other. So each of these, because of allowed to take trace, and then each of these pair A, B, the simple object allow, I can give you, write down a number, each of them. So each A, B have a number, then I can write down a matrix. So I want this matrix to be invertible. This is the modularity. So what about the T? The T is not mentioned, but I have still the T matrix. So the T matrix doesn't emerge in the definition of modular tensor category, but it's part of it once you have the invertibility, which is mentioned here. The T matrix is basically defined by the ribbon structure. So remember, omega is ribbon structure. Then because it's the natural isomorphism, you can write down omega A is actually equal to a scalar identity of A, right? Theta A is a number because it's a isomorphism, it's a scalar. But in fact, this scalar is really marvelous result. But anyway, we don't need that yet, but nevertheless, we have the following assignment. Once you write down the big S and big T by using the modular data, so then you can put such assignment. We call the modular group small s and small p. You make such assignment. There's two elements, right? If the assignment is satisfy the relation, then I can make out a representation. But they are not they don't satisfy the relation, but they satisfy the relation up to a scalar. So therefore, instead of representation, you get a projected representation. So this is you can say it's a bad problem, but this is life, right? So you just have a projected representation rather than, oh, yes.
The matrix has something to do with partial trace.
You can say this way, it partially trace. No, the theta is like, this is omega A, right? Because it's from A to A, right? Then I can pick trace. This is the theta A times dA, basically, another number. So theta A is the basic. They call it the twist. A lot of time I just identify these two, but I don't want to. I don't want to make people use. I mean, not sure. But anyway, this is a projected representation. This is not ordinary one. It's up to a scalar is a representation. That means that the two collaborators will be involved. I'm not going to mention it, but there's a 2%. So now, but then it's projective. I can lift to ordinary one. So basically, maybe I can draw here. I have a SL2Z here, and I go to 3L. R is a number simple object by using this row tutor. But if I forget about the scalar, that means I get a PGL. Right. So a projective representation can be realized as a homomorphism from SL2Z to PGL2 R. So this is actually my row tutor. See, this is actually the I write here as a just an assignment. S go to a matrix big S and T go to big T. But if you forget about the scale, I get the group homomorphism. That's what I mean the projective. So in fact, it's group homomorphism from the SL2G to the PGL2 R. So I want to lift it. So I want to put a row here. I call this pi. So this row is a lifting. Any such a row is a lifting. Does it make sense? I want to lift to an ordinary representation. This is good. Diagram of maybe commutative diagram of homomorphs. All of them go homomorphism. So the word projective is absorbed into this part. So I want to lift it. Want to deal with ordinary one instead of projective. So you can see this composition in row 2 basically is this. So the lifting, well, I should not say the lifting, the liftings are not unique, they're remaining. So but it doesn't matter. This is the main result of the paper of Don and Ling. Every lifting row of row 2 C is a congruence representation. So you lift it, still congruent. So no matter which one you lift. And I can tell the level between which SL2G minus factor fluid given by the order of row T. So you can factor fluid. And you know which SL2G and what SL2 factor fluid, which is given by order. So now how do we apply this result to the VOA setting? Well, when C is actually the V mark of the next VOA, then the associated representation, this is the Joule's representation of modular invariance, in fact, it's a lifting of the projective representation. It's not the projective representation, but it's a lifting. So the lifting is in fact given by the central chart. So because of that, then you apply this categorical result to this setting, you have a resolve the problem. This is how it works. The key, in fact, is the modular tensor category behind the VOA. So I just want to highlight one direction, one motivation of studying modular tensor category. In fact, this is another motivation by Jones. This is mentioned all the time. Every modular fusion category can be realized by next VOA. So how far from any progress of this result or conjecture is very little. We know that if the modular tensor category is so-called pointed, it means like every equal object has dimension 1, then the VOA can be realized with the call the lattice VOA or the lattice VOA. The pointed modular fusion category can always be realized in super lattice VOA. There are others. So, but this is kind of like zero step. This is I think is a goal or rationale for you between subjects. The other question is like which congruence representation can be realized by a modular fusion category as a lifting? Well, this part is completely unknown. Shall we study this way? I don't know, but we need to know at least some example. I mean, you cannot just, unless you have a big theory behind, I don't know. So we start from scratch. I don't want to know which congruence representation SL2 can be realized by the lifting of some modular fusion category. And if I know it can be realized, can I recover the modular data? So this is both of them they're related questions. So whether we can or we cannot, I need to decide if we can, and I want to realize. I want to write down the modular data for this representation. Is it possible? It looks like it's not possible. This is actually my impression. at the beginning, I think the second question is kind of a dream. But after a couple of years, it's not a dream. I almost always can do it. I don't have any kind of example. So that means I can always do it. So far. Maybe when the representation is larger, I cannot. So let's look at some examples. This is a concrete example. So this is group SL2 PC. That means I have a representation of congruent, every representation is congruent representation of SL2B. It's R prime. I can write down the character in this way. I don't want to give you the character value or whatever. I just tell you the dimension and the number of possibilities. So I write down the character 1, eta, psi, theta, c, psi, and then pi. So the one means the trivial representation. That's only one thing. But eta I, there are two of them. Ci have two of them. Eta I has 3 that's dimension 3 minus 1 over 2, and Ci has 3 plus 1 over 2 dimension. So in fact, I had only 2 possibilities. They actually parameter, 2 quadratic residue and non-residue. Mod P. The only 2 types of residue. Non-residue, residue. So I is the basically 2 possibilities. The thing that I is different. They have P minus 1 over 2 possibilities. And psi has dimension P, there's only one such thing. And chi I is dimension P plus 1 has more P minus 1 over 2. So just roughly mention about the character, I shouldn't say character table, you can just character property of SN2P, PC. So if the input is like eta I can always realize by this kind of quantum group of half of the quantum group. So we can always do it. It's a result. So it's basically called transitive. The other one is if you AI the state Ci, then you can always realize by quadratic form if the product will be correct. That means both of them are residue or both of them are non-residue. I can write down the corresponding representation as a real representation of the quadratic form from CP. So that means like there are only 2 quadratic forms in P. So they correspond to these 2 representations. So that means I can still, at least I have some pair to there. Now, if you take psi, there's no such realization. It's also proved in one of the paper, mine with Alexanderson Award. Now, if you put the theta I, this one is the this is the old version. Whatever I feel bad now. Okay, this is the older. Whatever correction that I made this morning did not happen. So let me just. Okay. In fact, what I say is the last part is a P 1 to 5 more 6. And P less than 25, 23. And this can be real. No others. For anything less than 23, it has to be this. And there's no, I don't know any example beyond 25, up to 1,000. So I don't know what to do with that. So yeah. We do not know. We do not. But we know up to here. 23, there are only 4 parts. What does it mean here? I don't know. Something is going on that is unclear. So why 23? Unclear. But anyway, let's throw out this example to let you know that in fact we don't have a overarching idea what's going on about these characters and representation for the modular data. Now, this is an example for you, like what I try to do here. So, which one can be recovered and what kind of pattern? So now I want to tell you some arithmetic problems So I want to mine something, right? I need to have a sheet. I need to have a filter. What are the filter? Coming from the arithmetic property or arithmetic rigidity of modular data. So these data will transpire to representation, the congruence representation FFT, or the corresponding listing. So like let us see be the modular data S of C, and we know that each row has the same length, this one. So I'm not telling you this is well known, at least known to us, and I could say it's a theorem here without telling you the source. It's known for a long time, but I don't know who proved it. So first, let's say. So the thing about S matrix, the length, so S matrix, I just wrote down before, they all have the same length. Each row has the same length. So and the length is called square root of dimension C. That's this length. So and then we have a Frobenius formula. I certainly did not correct a mistake here. I did correct a mistake, but I didn't give you the right version. So this is a J here, obviously. 0 is a unit object. 0 corresponds to unit object. And yeah, obviously S I0 is always non-zero for all I. So otherwise you cannot divide. So that means that the row corresponds the row corresponds to S matrix. The unit row corresponds to S matrix in the current. The unit row in the S matrix has non-zero entries. So, but then this actually is the arithmetic equation. The S actually is kind of arbitrary complex number. The Nijk in fact is a non-negative integer. So you can see that this is actually a very strong arithmetic rigidity for the modular data purposes. So the other one is this is the square root. Remember, we have the length of the S matrix, each row of the S matrix square root dimension C. If you divide out the entry S0I, it's always an algebraic integer. This is proved by adding of the object. So it's not arbitrary number, the algebraic even as an integer we take both. So if you do Sij over S0J, it's always if this one is even proved earlier. It's by physics. The proof is rigorous. At least I read it. So it's rigorous.
What is the length? Definition of the length?
The length, what is the length? We call it D, so I don't think I answered the question. This is just a number. So what is the length? In fact, the square of the length is the dimension of C, summation of DI.
It's telling you what the length of the matrix.
No, the row.
Oh,
Each row has the same length. I cannot say
row vector.
the row vector. Just like it's a complex.
Sum of F5 or well.
It's just the usual complex vector. You can compute the length, right? To make sense, I may not present it very clearly, but anyway, that's what I mean. So they show that these are good integer. It really has more rigidity than a good number, a lot more. So now then, because they are integer, then I can do Galois here. So, well, because I don't know where these numbers sit, it could be very large, the extension could be very large, could be very small. We have no clue at that point. So if you take an absolute, then I think the absolute Galois group element. So sigma belongs to Q bar. Then I can apply to this is known for a long time. So if you apply sigma to this function Sij over S0J, you can find another element I call sigma hat J. So that this equation holds. This one is known for, I think it's by Cauchy. So therefore, that means each of these Galois automorphisms define a permutation of the differential pair. From a very big group, this is a huge group, and then this is that means this subjection. So what we do is like the following: we just confine this to actually show that these numbers, in fact, in the well, this Dn like this. My convention is this, it's like e to the 2 pi I. I just write this instead of so to me these you can use the T matrix to confine where the where these algebra integers are. And then instead of using the actual Cauchy, I can use a small Cauchy. Then we know the Cauchy actually the reading. So this one advantage will be used, the active use. The other one is all of them are arithmetic in nature. So you take a dimension of C, as I said, this is an integer, and then you take norm will be integer, and then the order T is also an integer. Then they have the same path. So I keep using this statement, never prove it, but he all prove it. He wanted to know. So he wrote some notes on this, but I always so the norm of dimension C and the order dimension, the order T have the same prime factor. Not same. But then multiplicity could be different. So these actually play a role in the future. Yes. Now then we transpile this condition to the lifting now. So one of the conditions is like S is symmetric. So this is known for a long time before the modular data S is symmetric. T is diagonal by definition. So the lifting has to be there. The lifting actually just divide our scalar. The lifting will just rescale the matrix. So we can see easily that the lifting is always unitary. This one problem needs to be proved, but you know it because I said the link of the same. S is unitary. The T matrix is also unitary. Because it's Martha's result, the standard order. So then you can see that like a rho is always unitary, rho is symmetric, and rho T is diagonal. I need this. I need this. In fact, like I call this kind of representation symmetric. So and then you suppose you have two of these lifting of the same rho C tutor, and they are only given by a linear character. The linear character is of degree of order 12, but it's degree 1. It's just linear character. Simply because SL2Z hat, which is a linear character of SL2Z, it's D12. It's known, it's not something that we discuss. So now this is the main result that another main result that we proved in the paper, which is like rho defined over rho lifting is defined over this Q. It's not even Z. This is Q. I mean, it's defined over the cyclotop field psi M, where M is order of rho T, which is consistent with the previous case. So, but then it will be bigger than before. And then you take the Galois program. Now I can restrict to this QM. Then I compute then when sigma apply to the zeta M, it will go to zeta MA, which is Galois homomorphism. So then I compute the inverse of A mod M, which I call B. Then I can write down this operator. D segment. This is what basically it's like TS inverse, and then the ABA. And this indeed gives you a representation of Galois. So the Galois representation. So sitting inside, and moreover, if you this D segment is a sign permutation matrix. So the sign is hard to define. How to determine? It's difficult problem. But the permutation sigma hat is we talk about it's given by the Galois homomorphism. So we know sigma hat, but the sign is something that is really hard to. It depends on the category, but in general, it's hard. So this weird combination is 0, 1, and negative 1, basically. So it creates another row here, so you can use it to solve the equation. It's only 3 probably. And then sigma square is equal to conjugation. So this one, actually, this D0 sigma was discovered by Xiao-Gang before. Basically, you apply sigma to row S, this row is anything. You always get the row sigma and row S. So what we did not know is the second sigma square. So it's also one of the open problem in this. So now, from now on, I just don't want to refer to the modular fusion categories sometimes. So I just call a lifting of rows imputed for any modular fusion category to be empty representation. I don't want to refer to sometimes I do. Sometimes I don't refer to them too. When I say empty representation, that means it's some lifting of rows imputed for some modular tensor category. Now we can begin to build our mining machine. So I could tell you the motivation, tell you some of relative rapidity or the filter that we're going to use. So we start to build the mining machine. I refer to mining Bitcoin as mining modular data. It's not worth anything. Maybe if you think it does. I try to mine it from where the input is the character. Just any character of SL2Z more NC. The output is the possible model data. So this is the mining machine. So look, maybe this is the prototype of my machine. So this machine, you can see that for small degree character, it will work probably. When the degree of the character gets bigger, you get some trouble. Basically, computer resources. It takes forever to do anything. So let me just look at this. The machine, let's say, look, this repeat example that we talked about. Let's say chi is a reducible character of SL25, we talked about SL22 before. So let's say I look at, in this case, I look at degree 3, degree 5, and 6, depending about the probability, and then the output is like, there's no such thing. The output will be empty. You cannot get anything. And this is the no modular data can be realized. Can realize these the representation is even equivalent to this representation, or no empty representation equivalent to this representation. So if you take like the degree 2, remember the degree 2 of eta I of dimension 2, there are 2 of them. I will generate 2 of them. There are 2 outputs. One is like the first one is this one. Second one is this one. This is the machine. Maybe I just like right here. So I have a machine here with my black box. So the input is like degree 3, 5, 6, SL25. I get nothing. If I put in like my machine like will give me like if I like put in AI, I will get like 2 possibilities here. These are this is one give. There are 2 sets of data, SI. Each of them will give you. In fact, each of them will give you 2 of them. So more than 1. So this is not just one, it's 1 to many. Could be empty. So the goal is like, you can see that we want to discover new modular data, right? Let's say, or we want to classify all the modular data. What do we do? Because it's still small rank. What do we do? Well, I know all the reducible character of SL2C, and then we can put it together to form a representation of certain degree. And you can all use this character to build our modular data or nothing. So it's completely exhausts all the possibilities. The problem is sometimes it may not be realized. So now this is it. Well, you want to find the input. So I want a symmetric representation. So fortunate or unfortunate, every character of SL2 that is MFC can be afforded by a symmetric. So I cannot do anything, but I have to consider every complex representation, a radar corresponding to symmetric representation. Unfortunately, we are able to use we use a paper to build a gap package. So we can use the result of build gap package which generate all this symmetric representation. Not very large. I put less than 100, maybe around 100. Depends on your level. The level is too high, then you probably have less. The level means n. Well, a degree. The degree you cannot generate too large. If when n is 100, then the degree cannot be. It kind of like come up. Now, the symmetric input allow us to use the following result. Basically, if I have a metric representation of SMT3, which is vector concrete, then which is equivalent, not even equal to equivalent, that means up to conjugation to a empty representation. First of all, I can rearrange the order of the basis element so that rho t equal to rho prime t. I can always do it because it's just a permutation. So orthogonal, so I can do it. So there exists a real orthogonal matrix U such that the conjugate of the character that we input, it will go to the one that we intend to have. Now remember that we really don't have rho prime here. We assume that's one. And the second one is you commute with this rho t and rho prime. Now, when rho t is equal to rho prime, you can see that the second equation implies that it depends on the multiplicity of eigenvalue. If the multiplicity of eigenvalue of t is each of them has multiplicity 1, you can only be plus or minus 1. It's the diagonal matrix, plus or minus 1 diagonal matrix. So that means rho prime is always the same as rho s. So that's a sign. So this means like if the representation is highly non-degenerate, then I can almost get the real one. If it can be real or it's not real. So this is actually the plus part. So in terms of, so we are very happy with this package. We almost get 3 for 3 sometimes. Now, then if we cannot nail down that there's a there could be degeneracy in the eigenvalue of t, then we need to have a known matrix U there, which is unknown unit, one unknown orthogonal matrix. Now you have to solve the unknown orthogonal matrix. So how do we do that? We don't have an equation. We don't have rho prime. We assume there's one. What do? We want to conjugate, update the conjugation, satisfy all the properties that I mentioned arithmetically. You solve it. You use the property to solve the equation, not the equation. You use the property to solve the equation. So, that's why at the beginning, I don't believe we can solve it, because you don't have an equation in the first place. Yeah, just have property. But we can solve it for whatever reason that it's not clear to us. So we need some basic result to do the small thing, which is the first one is the ideal significance, because we cut down a lot of representations. So suppose I have empty representation, a genuine one, empty with couple modular data, or modular diffusion category, has a non-trivial decomposition that just decomposes a representation. Then you can still look at the spectrum of rho 1 and rho 2. Right? If no matter how you decompose them, the eigenspace of these two, the spectrum of these two sub-representations have overlap, non-trivial overlap, at least one. So, but then if you have 3 of them, then suppose you decompose into 3 of them, then any 2 of them, you can see the combinatorial effect, the purely combinatorial problem. So this kind of problem is very good for machine. It's not good for human being. So you look at this. So you input a machine, the machine can get to the answer very quickly. When you do it by yourself, you can do it. Just get easy. At least I will. So the second one is easy to do with the small one. It's supposed to have 2 non-degenerate means that eigenvalue t that have only multiplicity 1. So I have rho 1 and rho 2, both of them non-degenerate. But they can overlap, but each of them individually they are non-degenerate. So such that rho 1 plus rho 2 is an empty equivalent to an empty one. empty representation. That means I have an empty representation which can be decomposed. Then the modular data in this case can be solved explicitly if the following conditions hold. So we can actually solve for both. If the eigenvalue of the row 1 and eigenvalue of row 2 have only one overlap, that means synchronous. This one that can solve it completely. But I require row I to be bigger than 1 dimension. That means it cannot be just one contained yet. The second case contained it. Well, if one contained in the other, strictly contained the other, and they have opposite parity. That means if the same parity, that means s squared is equal to 1, s squared is equal to -1. This is the parity, but it may not have a parity, so then it doesn't have parity. Suppose they have parity and opposite one, then you can solve it completely. So these are the cases we can solve explicitly the modular data if it exists. So if the modular data exists, we can write down the modular data may not exist. It still may not exist. So what I was saying, I can write down the solution may not be a modular data. So let us look at one example. This is the example that I think will illustrate the first case. This example of G2 level 3, the outcome. Of course, at the beginning, I don't know. After I finish the computation, I know. So I start with level 4, degree 4, level 7, and degree 2, level 3. That means it's a representation of dimension 4. It is a representation of FF2 equals 17. Makes sense? I put subscript 1 here. That means I have a list 1, 2, 3, 4, 5, and so the one doesn't matter. One of mine, and second one 2. So I write it down. I write down the T matrix. Now this is the 4 degree 4 T matrix. This is a 7 square 7 raised power 4, and the other one is 1 say 3. You can see that the spectrum has only one overlap here, 1. So I write down the corresponding S. This is the S for the first block, the S for the second block. Write down. Then I just claim that to solve it. Because indeed, this one can be written down directly immediately. So you can see that by the beginning, you can solve for rho S with the sign. This is a plus or minus, and you can see it's kind of a obscure one, but it's not. So I write down this result. As long as you understand how you operate this theory, you can write it down. Now, what about the sign? The sign actually can be determined with this thing right down in this way. So you can see that if it's a unit row, the corresponding row has no 0 entries. So this cannot be these 4 row. The unit row can only be the first 2 rows. I don't know which one, so I can pick one. And then I can find the other one's called Frobenius-Schur dimension. I can figure out they are these. So once you figure out Frobenius-Schur dimension, you can try that. So basically, each row will give you one type of epsilon. So each choice of unit row. So there are 2 possible choices of unit object. So there are first 2 rows. And each choice determines the object corresponding to the Frobenius-Schur dimension. I can tell the third dimension once already on the unit. Then which is sign the sign. So can each choice of unit object determine the sign? I can write down the completely. So end up the G2 level 3 and the Galois conjugate. So do I know? Can I deduce it? No, I just know it. I just know it matches the G2 level 3. That's it. It's not something that you can deduce. I can write on the modular data. I find something that matches it. It's realizable. It's just something legitimate, right? I still don't know it's legitimate. So this is actually the drawback because there's no associativity before. The modular data can be fake. So let's look at the other example. This is a down example. I think it's more. So this is actually a sum of really irreducible. Degree 3 level 4. Degree 3 level 4. Degree 2 level 3. Degree 1 level 2. So this is the notation here. Degree 3 level 4. Degree 2 level 3. So again, I wrote this one. So now I can write down use that program to write down the representation. So I write down row SS, put it there. Well, I put it there means like they put it as a diagonal blocks. And then the other one is the T matrix, go there. So basically, the first three is this one, second two, this one, this last one. Now, you look at this, then you can see that I can divide out into 3 and a 3. You can see now this is 1 negative 1 I, 1 say the 3 negative 1. So you have 2 overlap this time. It's not 1 overlap. 2 overlap. Still can be solved somehow. I just don't have a theorem. I still can solve. So I don't have a theorem, but still can solve it. And so you put it this way, they're both non-degenerate. This is the first block is non-degenerate. The second two combined together is still non-degenerate. So solve it anyway. Assume it's again, I assume it's equivalent to empty representation. I do not know this empty representation at all. I just assume it's there. Then I basically solve by property rather than the general equation. So then you can still solve the SN2 matrix. This one is even more explicit. No ambiguity at all. So the S matrix completely solved. The D is there. 2 times square root 3 minus 3. No ambiguity term. 0. The T also written down. It's already there. It's just original. So looks like I have a legitimate one. So we check. One thing I did not mention is to check is called the Frobenius-Schur indicator. So anyway, I have 2 possible choice of unit rule again. I pick one and then solve it, and then I write down the corresponding Frobenius-Schur dimension. I can write down any. I can pick the first one as a unit rule and pick the second one as a unit rule. Once you pick it, and you can use within the formula to write down the fusion rule. So you can write down as you can pick the fusion rule, and then I pick the 5th object. So the reason I pick the 5th object because we checked it already. So you can compute it. These fusion rules are non-negativities. For whatever reason, it works. But you can compute the Frobenius indicator now. So far we don't have involved any associativity. So the Frobenius indicator actually took up some take up some part of associativity character. So you use the second indicator to compute it, then you can find it. Like the second indicator of any object can only be 0, 1, negative 1. And we have a formula to compute it. So now we all involve modular data, just plug in it, and you find something like the 5th object has indicator 2. This is the only reason that we get this one. That means the no associativity can fit into this modular data. That's what it means. Although everything is work fine, but you will not be able to find associativity makes it work. So this is the part there. Now, this is actually extreme case. How many of these exist now? Not that many. Only one. We face only one. It's very, but when the rank is very high, we don't use Frobenius-Schur indicator actually. But anyway, this is all example that I want to mention. So we finish the rank 6. Because of that, the paper rank 11 is still incomplete. So we under review, although we say in the archive, but I will mention it. So one thing I want to mention is that there's no new modular data, first of all, for rank 6. But actually, Wang actually, Xiao-Gang Wang actually computed this, published this paper before, this classification before, except the last one. But their method is his method was different, and he also assumed super unity or unity. The last one is not unity. So this is complete. This one is certainly complete, including the non-unitary. And secondly, is that he assumed that the fusion rate coefficient is equal to 3. So that means he could not tell it was complete, because unless you can show this stuff about. So that's the reason that we start with this mathematically with the computer have to solve the problem. Now I want to move on to the higher rank. We'll take long. So the classification rank 7 is relatively easy to settle this fine. Not very true because we cannot decompose as a daily product. But as nothing new. For non-integral modular data rank, they're all realized. One new thing appeared, which is the Lie group. Now, a Lie group is a very interesting story in the list application. The dimension is always largest in the list. Well, for whatever reason, they are the largest one. So you just line up all the global dimension. They are the biggest. So this is the actual, and this is the Lie group involving group 5, and the coefficient 5 is the one in the list. Now, the pointed one, they always say, so we don't care. But the non-pointed one also comes from a group. So I write this down. It's not, I don't want to explain it, but I just wanted to see the all involved group in cohomology. That's what I was saying. S3, D2, whatever. So the other non-integral, the other non-pointed integral module tends to come from the double of S3, and then you do some tensor product over. So I think there are 8 of them. Okay. Now, move on to something. There's a modular data rank line on this dimension. We believe it's also at the beginning of notes. And we went to a meeting in them, and then Xiao-Gang said, like, this actually modular data of this Lie group of different parameter, and you double it and you take that job. So really not obscure what we didn't get it, but it's also one of the others. These are all involved Lie group projector modular data, the double particularly. And this also double. You cannot have the Lie group itself institution. You do something, you get it. Now this one is we just like recognizing example. Put it there. We move on to rank 10. This one is even more. We still don't know the answer. This is also the largest. 720 per square foot. If I say if because we don't know. If it's a general modular data, it will condense. When I say condense, it means like you just look at the condensation. We call condensation, they call local module, whatever. It is actually pointed one of the three. I think it's a 3 form. So I think I did the other one. This one is coming from the Hager. I think also Hager. There are 2 types of Hager. One self-built one. I think this one's not self-built one, but I don't know much about it. I want to know, but it looks like not most people, even in those people with some practice. So this one is still, well, we have an idea, but don't know what. Because there's another one of the similar dimension can be real. Now, this is the last one that we have here in our list. Is rank 11 modular data. I don't even want to write down the theoretic form because it's no longer quadratic. I think it's quartic. It's a degree 4 of the integer. It's also the largest in the list. It's the largest so far in our list. And the order T is 35, and we have no idea this. I don't know. There could be some opinion now because of this. Some say yes, it's this, some say doesn't make this. Basically, just opinion. Usually, it's got. But I don't know this one. We need some method to explore. So maybe we go to the very end. I just want to mention there's some other. Okay, as I said, by evidence. So there are some other integral case like some is done by Kaku, and I think you can also say the cutoff is already even the 13 is solved by and then basically the 12 you can obtain a similar result. There's no new integral modular data. So the integral modular data they approach. I personally don't estimate much of it, but I use also use Egyptian fraction to solve. But I think there should be other way, but I think it's still efficient on the low rank. I mean, like probably you can go up to rank 16. Somehow simply we can go to rank 16 for the interface, even for it's not going to be the case. But so far we're still cleaning up a program to do the 12. We finish the 12 with a clean program, then we can move on. Excellent. So in short, I think there's no new physical motor data that is not realized. All of them can be realized. I know two. So the 31 maybe could go better. Because we haven't get to it. I think we can even stop. So we still stuck in the 12 one, we clean the program, finish the rest of the 12. You can see I didn't have any information about 12 because they run. I stopped it.
Okay.